Okay, I've gone through this exam several times. Are there specific questions people have, or should I just go back and start at the beginning again? Did you raise your hand or? Okay. The what? Oh, the written questions. Yeah, those are quick, so we can do the written questions.
Time. New movie recording.
Okay, we're finally ready to get started. So the request was to go over the written questions. So we'll start with that and then we'll wrap around, or I'll just go to wherever people have questions. All right, so key compression. What is index key compression? What are the two necessary conditions for using index key compression? Does anyone know the answer to this question? Go ahead.
It's like a way to save space by separating into prefix and suffix. So multiple people have one prefix and out into.
Yep, that's exactly what it is. That's exactly what it is. So key compression. As I said in the past, database. Database key compression. If you go, you'll actually see this diagram is in the lecture notes. Remember, I said that you can use Google and other things. Basically, key compression is, best example that I can think of is, suppose that you had a key that was last name followed by first name. So it's a compound key, it's last name followed by first name. If you just used sort of standard keys, standard approach to keys, you'd have, you'd have an entry Smith colon John, then Smith, colon Bob. So you basically would have an entry for every last name and then the corresponding first name. So would be lots of people named Smith. So instead of doing that, what would happen is you would have one entry that was Smith, and then that in turn would point to the first names. So if you had 1,000 people whose last name was Smith, what would happen is you would basically have one entry for Smith and then just the ones for the first name, as opposed to repeating Smith 1,000 times or 100 times. The name one's probably not a particularly good example. And of course, this is not my day.
It's not. What is he doing?
We should do some before we leave.
All right, so
We should. But like, what are we gonna do? Quick time.
so that's the first thing is so the key has to be compound.
Bye.
So it has to have at least 2 segments. My example, it's last name and first name. So requirement number 1 is that it's got to be compound. Requirement number 2 is that there have to be a large number of repeating values for the first part of the key. So my name 1 handles that, which is the key is compound, it's last name and first name. And if I had 1 million entries in there, I'd probably only have a couple hundred last names. Not that many distinct last names. So I'm going to have the same values over and over and over again. So instead of repeatedly storing those values, I'm just going to have a single entry for each of the first fields. And that in turn is going to point to the index entries for the second part of the key. So that way, I'd only store the 500 distinct last names as opposed to just storing the same last name over and over and over again. So that's what key compression is you look at the prefix, the beginning of the key, the first segment or the first and second segment, and you determine, are there a lot of repeating values? And if there are, basically just have one entry for each of the repeating values, and then that in turn is going to reference the ones that are the second part of the key. And again, this is a real good example. And so we went over this one in class. This is actually a little tutorial about it. But you can see it's exactly the example, kind of that I covered, which is Jack, Marcos. So these things occur. So that's going to point to a single entry. So instead of having this one twice and that one 3 times, it points to an entry, which then basically it points to a prefix table, which then addresses to the suffix. So that's all key compression is. And the easiest way to think about it is just with last names, which is if I had last name, first name, I would just have a single entry in here that was basically the prefixes. So I'd go to the prefix table and say, okay, go find Smith, and then that in turn would go find all the entries that had Smith in it. That's all key compression is. All right, so is that clear to everyone? Does anyone? All right, it's pretty straightforward. So now let me go get my notebook open again. And it's going to be Dropbox. Columbia course, courses, also maintain that exams, final exam. Don't want to restore my pages, so no. Don't want to restore my pages. All right, so let's get on and take a look at the next one. All right, so that's key compression. Hash versus tree index. What are 3 reasons to use a B+ tree instead of a hash index? Does anybody think of any? I'll settle for 1 at this point. Yes? So the first answer is, so very good. The first answer is, if you are, think about a where clause. So you're using a key to kind of accelerate lookup with a where clause. A hash index is only going to work if the operator is equals. So it's equality. So if I had a hash index on last name, first name, the only where clause that would work would be where last name equals something and first name equals something. So I need all the fields that are going to make the key, and the only comparison operator is equality. Anything other than that, it doesn't work. So if I wanted to go and just find all the people with last name Ferguson, I couldn't do that with a hash index because the hash was on last name and first name. So you need the entire key. The where clause has to have all the columns that make up the key, and it's got to be equality. So that's reason number 1, is it's just much more restrictive in terms of the kind of queries, the kind of where clauses it selects, it supports. So that's reason number one. Reason number two is you can kind of build out on that. If your query has got any kind of range in it, like where last name is between Smith and, you know, Tango, you need a B plus tree for that, because you are checking on basically saying, go look for these things in order and go find a segment. So hashes are not in order, B plus trees are. So anything that's a relative comparator or a range, you need a B plus tree for that. So that'd be the second reason. And the third one is kind of, it supports like. So it supports like clauses. So if you were going to say select star from, you know, people where last name like FER % to match the rest of it, you can do that with a B plus tree. You can't with a hash. And then a fourth reason would be if you were ever going to do anything like order by. So you're going to try and order the results. So number one is you have to have the whole key. You can't have part of the key. Whereas with the B plus tree, the where clause doesn't necessarily have to have all the columns. The second one is range operators, comparative operators as opposed to equality. The third one is like, you can match patterns. And then the fourth one is if you ever want to do order by. So those are the primary reasons why you would use a tree index versus a hash. Is that clear to everybody? Does everybody understand those things? So are you just transcribing what I'm saying, or do you actually remember what B plus trees are and go, oh yeah, that's right, you talked about that. All right, so yeah, that was a question. Yes.
Okay, so are the first two reasons the same? So I think you mentioned where clause has to be equalities, and then it becomes range.
So if I were going to break it into three orthogonal reasons that had no overlap, number one is if it's a compound key, you must have all of the fields. Reason number two is a B tree supports comparative operators, hash only supports equality. And the third one is order by is very common in queries, and you can't, B plus trees are ordered, hashes are not. So if I had to pick three that were just completely orthogonal, those would be the three. All right.
I have two questions, please.
All right, so everyone understands that?
Yeah, I have two questions, please.
Query processing. Give 3 examples of rewriting a query to produce an equivalent query. So anyone, can you give me one example? Yes. Can you speak more loudly, please? Yeah, so I would have phrased it slightly differently, but yes, it is. So these are some basic rules, which is, go back in here and do it, make it a little bit bigger. I'm actually not going to use the wonky notation, but right. Join. So select, I'm going to capitalize it. Select of join of A comma B is equal to join of select on A, comma, select on B. So you could push the select through the join. It's literally what it's called. It's called selector pushing. If you go back, remember from the first lecture, I said SQL is an algebraic language. If you kind of take a look at that, that's literally the distributed law for multiplication and addition, which is select distribute. So that's reason number one. All right. And obviously, This one's going to form the Cartesian product. So if there's 1,000 in each of them, it's going to form all 1 million combinations and then figure out which ones match. If one of these is very selective, it's going to go in and say, like, if you're just picking people whose last name is Aardvark, one of these sides might only have 2 or 3 things in it. So that's selection pushing. I would also accept this one, which is project of join AB is equal to that. So that project falls into that category. Be an example. Now, this isn't good. Why would I do this? I mean, it's not going to filter out rows. There's no select here at all. So why would I push the project through? Well, the answer is this table's got 100 columns. This table's got 100 columns. The answer is only looking at 2 for each of them. Why am I loading all the data? I can just load the 2 columns from A and the 2 columns from B, which means I'll get more tuples in memory and I'll do fewer IOs. So this one is CPU, basically its performance. This will reduce the N by M factor in terms of actually executing the query. This one means since you're not loading data you don't need, you can get more of it in the buffer pool, and when you're running the queries, you're less likely to get a buffer pool miss. So that would be an example. Third one, join of A comma B is equal to join of B comma A. Join is commutative. Why would I do that one? The obvious answer is there's an index on B, but not on A. Or sorry, the other way around. I want an index. Yeah, there's an index. There's an index on A, but not on B, because remember, the left one is the scan table. You always go through the scan table exactly once. The right table is the probe table. You're going to go through the probe table once for every row in A. Right, so if A's got an index that I can use, I want to scan B and probe A on the index, as opposed to scanning it. So let's just assume that, you know, it's a binary index. There's 1,000 of them in both. This one, if I scan A, I'm going to have to go for every tuple in there. I'm going to have to scan B. That's 1 million. If I swap them, I have to go through this 1,000 times, but 1,000, log of 1,000 is, depending on what it is, you know, it's 3. So on average, this one's going to actually do 3, not 1 million. So it's going to be 3,000 versus 1 million. So that'd be an example. And there's a bunch of them that you can do, but those are the 3 canonical ones. Is you can push through. There's other ones. So those are the 3 that I went over in class. And they're kind of the 3 classic ones. You can also Google SQL identities or SQL rewrite. There's hundreds of these things that they've come up with that a query optimizer will do. Buffer management. Explain force, no force, steal, no steal buffer management policies. All right. Force is when the transaction is going to commit, I force any dirty data in memory to disk. So if you touch, this transaction has touched 2 pages, 2 blocks. I push both of those blocks from the buffer pool back to disk before I commit the transaction. The reason I do that is durability. I don't want to think I committed the transaction, but keep the data in memory, because if I fail, I lose my volatile memory. So I thought I committed a transaction, but I pushed the data to disk, so it's not durable. No force is the opposite, which is if a transaction commits, I'm willing to keep dirty blocks in memory. Why would I do that? Well, the answer is blocks are maybe accessed by multiple transactions. If I can figure out a way so that 20 transactions update a block in 20 different places, but I only write that block once, I save 20 IOs. Whereas if I force every commit, if the transaction touches 4 pages, every commit is going to force 4 pages. Whereas if I keep it in memory, I may save some writes because I'm going to, 2 transactions are going to hit it. So that's no force. So keep it in memory. The question is, how do I make it durable if I keep it in memory? And the answer is, I write the log record. So all of the transaction updates are going into the log. So I don't force the pages, I force the log record, the log block. So before I will say transactions committed, I'm going to force the log. But the log is shared by hundreds of transactions. And so that's kind of amortized over lots of transactions. So no force is I keep dirty data in memory. I force the log page, but all the transactions are using the log page. So no force saves a lot of write IOs. Just right. Steal and no steal. Well, no steal is if I've got a page that's got dirty data in it and I run out of space in the buffer pool, I need to go find a replacement candidate. I need to go find a page that I'm going to load a block in from disk and overwrite a page in the buffer pool. No steal means I will not take a page that's pinned and has dirty data in it. So if somebody wrote that page, I will not use that as a candidate. It's got dirty data in it. If I take it away, I've just basically lost. Steal is, I will do that. So no steal, steal. Steal is, I consider for overwrite pages that are dirty and pinned. No steal is that I do not consider dirty and pinned pages when I need to go find another buffer slot. So the question is obviously if there's dirty data in it and I overwrite it, didn't I lose the data? And the answer is that's what the log is for. Because I'm going to force it out on the log. Well, why would I ever steal? The answer is if I don't steal writes, the buffer pool will tend to fill up with dirty pages. And so if I've got transactions, a bunch of low priority transactions that are touching lots of frames, lots of pages, they're going to fill the buffer pool up. And eventually I'm going to run out of things to reclaim. And so what I want to do is I'm going to use the log instead. So I'm going to get better buffer pool usage. So that's steal versus no steal. Was that clear to everyone? An alternative answer, which is I will accept, is
is CG to 1%?
probably actually the PDF where I stole the diagram from. There's actually a picture in the book too. So you can look it up. It's not it. So anyway, that's what steal and no steal are. It's actually a section on it in the book. Let's go find images. So this is literally, I believe this is actually the diagram from the book. I want to do that. So let's go to a new tab. And so this is the breakdown. No steal, no force. force, no force, blah, blah, this is desired. Basically, the way you handle this is redo and undo. And so if you have to write a dirty page that's not committed, you write an undo record. If you overwrite a page, you just do a redo. And so literally, you just go look this up, but it's an optimization so that you save IOs and you get better buffer usage, because one of the key ideas behind the log in a database is the log is actually it determines the state of the system. It's not the memory of the database engine. So what's going to happen is if I need to recover the state, the first thing that I'm going to do is I'm going to replay the log, and that's going to determine which disk updates I have to undo, which disk updates I have to redo, etc. So it's the log. And the reason this is more efficient is all of the transactions are writing their records to the log. So when I force a log page, I'm forcing data from dozens of transactions, as opposed to when I force a log page, I've forced data from 12 transactions. If I commit and do force, I might have written 3 pages for one transaction. So it significantly saves read and writes. So that's what force and no force, steal and no steal are. Right? Hash index. Okay, don't think that's the one he used. One I used actually, that's not the one I used. There's a link to the actual one that I used in the lecture notes. No, that's not it either. All right, so anyway, I can't remember where it is, but there are 2 things, actually several things, but the 3 biggest things that determine hashing are the size of the hash table, how big is the hash table, the hashing algorithm, and then the rehash algorithm. And I give you an example. Table size is 11. Hash table sizes are almost always prime numbers. And the reason for that is I want when the keys coming in, I want them to hash evenly over all the hash buckets. So, I mean, I want the probability of when a key comes in, I want it to equally probably hash to any bucket. If it's not a prime number, I start getting into the fact that, like, if I picked 9, lots of things that have got 3s in them are going to hash to, one of those buckets, 3, 6, 9. So it's not going to be uniform. Whereas if it's prime, there's no common divisor, and so that's why they're prime. So, all right, I hashed these values, 11, 13, 14, 21. I'm now going to hash 24. So the hashing algorithm is modulo of the table size. So 24 is 3 mod 11. Right? No, it's 2 mod 11. It's 2 mod 11. So that one would go 0, 1, 2. It would go there. 24 would come here. That bucket is full. It's got something in it. So I can't use it. I have to rehash. The rehashing algorithm is linear probing. And what that means is that bucket is full. That bucket is full. Therefore, 24 would go here. So all linear probing is that if you try to hash into a bucket that's full, you just scan through the table until you find an empty slot, and that's where it goes. How would I find 24? Suppose I were trying to look it up. Well, I would hash it. It would hash to 2 mod 11. That's 13. It's not it. That's 14. It's not it. That's 24. So on insert, when there's a hit, I scan until I find an empty slot and put it in there. In lookup, when I hit, if it's not the one I'm looking for, I scan until I find an empty slot. So as I'm scanning, I'm either going to find what I'm looking for or an empty slot. If I find an empty slot, it's not there. And so that's how it works is if you don't have a hit, you don't basically have a problem, it just goes into the slot, it's obvious. On insert, if there's a conflict, you scan until you find a space. On a lookup, if it's not the one, you scan until you find a space. And so that is the hashing algorithm is module the table size, the rehash functions linear probing. Those are the two dominant ones. Like there's lots and lots of more sophisticated ones, but those are kind of like how a hash works 101. An example of one that is different is they'll do quadratic probing. So basically we'll say, okay, let's try 1. It's not that one. Okay, well, maybe I got a lot of them here. And now let's try, 4. So if you think about it, if lots of stuff have hashed at the same value, you're going to get a segment of these things. Like you kept hashing here, you're going to get a list. So sometimes what they'll do is probe it quadratically. They'll do other things. But it's what's the hashing algorithm and what's linear probing. 24. So it's going to be boom, boom, boom. And then 30 is, what is that? So 30, 22, it's 8. So it would go there. All right. So there's no cache hit. So you can actually see that I gave, this one has the answer. So there's 24 and there's 30. So that's what they got. Only reason I do this is if you're ever talking to somebody in a job interview or something and they ask you questions, these are the 3 things that determine hashing: table size, hash algorithm, and rehash function. The other factor, which is incredibly complicated, is this starts to break. So hashing, looking up something in a hash table is constant time. So you can see that, for instance, if I try and hash, 30 and look it up, I basically just compute the module. There it is. So it's constant time. What happens is that if I start getting these segments like that, it starts to go towards n. Now scanning. So you don't want this thing too full. And so there are all kinds of sophistication around when do you resize the hash table. And so it's the fundamental trade-off in computer science between space and time. If my hash table's got a lot of entries in it, it's going to be slower, and it'll start to approach a linear scan. But if I resize it a lot and it's sparse, then it's going to take up more memory. And so the fourth one in here is, fourth attribute of this is when do I resize the table? But I didn't I didn't really want to worry about that. Join optimization. Is that clear to everybody? Join optimization. Briefly explain a sort, merge, join. And when would you use a sort, merge, join instead of a hash join, and vice versa? All right, so anybody know what a sort, merge, join is? By this point, you should all be furiously typing, "Dear Google, I hope this homework, this final exam finds you in good health." Okay, what is the answer? Go ahead.
Sort, merge, join, sort, split, tables according to join issues, and then in a single pass.
Yes. Why would I do that?
So you only have to go through all the data points.
right? But the question is, how does that work? Okay. Fortunately, that was not part of the question, right? So here's the way to think about it. Whether I can. So we're going to go find this. So lucid chart. Again, right here. That's not it. Is this one lucid chart? That's not it. This is Columbia, so this one must be it. That's not it. Basically, the answer is, think about it for a second, which is, I sort the two tables. So now I know, based on the join keys, they're sorted that way. So I'm going to read one block from each of the tables in the memory. And I'm going to scan the block on the left. Because the right table's sorted, every one of the keys, I'm going to find them in the first block. And when I don't, I know it must be in the next block. So I get rid of the block that I have and read the next one in. I never have to worry about going back. So what's really going to happen is, for wherever I am, I only really need two blocks in memory, the left block and then the one I'm probing. I'm going to find the keys. I'm going to find the things I'm looking for in the right block. If I don't ever need that block again because I'm going in order. So I'll read the next block in. But the net of it is I only ever need to read a block from either table exactly once. You always have to do that for the scan table. You're going to read every block on the scan table once. With the sort merge, you're only ever going to read a probe block once. So it drastically reduces the I/O. On the other hand, if you don't do that and it's not sorted, if I've got 10 blocks and I can allocate 5 frames of memory, on average, for every row, 50% of the time, I'm going to get a buffer pool miss, and I'm going to have to read it. So it drastically reduces the number of I/Os. Now, the downside to that is you have to sort them anyway. So you have to read them to sort them. But you can do that in n log n time. So that's a 2-pass algorithm. If you do the sort, you can do it in such a way that you read far fewer blocks than you do when you do the join. So yes, you have to spend some stuff up front. And the reason it's called a sort merge join is basically you basically do a merge sort bottom up. So that way you're only going to read every block n log n. Basically the I/O complexity is n log n, whereas if you don't do that, it's n squared. So it's significantly faster to do the sort merge. All right, second part of the question is, all right, why would I do that instead of a hash join? Well, maybe I want the answer in order to begin with. Because if I'm doing join order by, then it's just better to do it that way. So that's the obvious answer to that. Other one is, in principle, you don't actually need to join on equality. You can join on comparators. It's very rare to do that, but the net of it is, hash join only works for equality and it can't be ordered. Deadlock. Briefly explain 2 techniques a transaction manager may use to break deadlocks. So what are the 2 techniques? really sucked, wouldn't it? Basically, there are two techniques. One is timeouts. So in a transaction, you can do it either on the transaction or on an operation. So we'll assume we're just going to do it on a transaction. If I say no transaction can run for more than a minute, obviously, if that transaction gets involved in a deadlock, it's not going to finish in a minute. It's deadlocked. It can't continue. It's going to exceed the minute. It's going to get aborted. And that will break a deadlock if it's part of the deadlock, because you had, you know, that waiting on something that was waiting on something. So in essence, you're just randomly picking one and aborting it. So that's the simplest technique, is just if something is, so basic theory of databases is if a query, query is or transaction is running longer than you think it should, it's probably not good. It's either deadlocked or the programmer did something stupid, but in either case, kill it. So that's the basic idea. The second technique is you build a wait for graph. So whenever a transaction requests a lock that conflicts with another transaction that already holds the lock, you basically in the graph say transaction A is waiting for transaction B. So if now next transaction comes in C, if it tries to request the lock that A holds, it waits for A. If it tries to request the lock that B holds. So it is a directed graph. The nodes are the transactions and the edges are which transaction is waiting for which. If there is a cycle in that, so if I can go from A to B to B to C to C to D back to A, I have a deadlock. And so it'll use a wait for graph is basically to determine whether or not there's a deadlock. And if it does, it will pick one of the transactions in the cycle to abort. There's a bunch of policies for how it'll do that. But in essence, the two techniques are timeouts and wait for graphs. RAID. What is a major advantage of RAID 5 over RAID 0 and RAID 1? Yes?
Since it uses like multiple
Yeah, that is true. So that would be an answer. Yeah. So yes, that would be true. The answer that I'm looking for is that the storage overhead of RAID 0 or RAID 1 is 100%. I always, basically, if I've got a block, it's always in two places. Just a question of, am I striping? You know, so exactly how am I doing it? So, RAID 5 doesn't do that. Basically, it uses correcting, you know, error correcting, and that overhead is 20%. And so it's got much lower overhead for availability. So it gets very high availability and very high performance with not very much overhead. So if I can never remember which one is which, but if you pick RAID 0, I think it is, you get twice the throughput, but you can lose data on a disk failure. If you pick RAID 1, you get high availability, but 100% storage overhead. If you pick RAID 5, you get high throughput and reliability, but the cost you pay is 20% data replication. So that's the main advantage of RAID 5 over RAID 0 and RAID 1. Do you have a question? Yeah, that's why it's 20, whatever, 25%. Yeah. Well, no, I mean, if I'm doing, I guess it's RAID 1, and I want availability, both of them have the block. So basically the overhead's 100%. 25%. No, it's because I've got 4 data blocks and 1 parity block. So it's 25%. Yes, I know, but however, it's RAID 5. Disk addressing. Briefly explain CHS addressing for disks. So what is, also back to your question about RAID, like what's the overhead? Clearly, we all now understand the concept. If I need to know the exact overhead, I say, Google, dear Google, right, what are the overhead of the various RAID technologies? It's the concept that matters, which is RAID 1 and RAID 0 use complete block replication to get availability and throughput. RAID 5, RAID 6, they don't do that. They get the availability without the complete overhead. So in the exact overhead, yes, you basically need a certain, but there's RAID 6, there's RAID 1 plus 6. I mean, so basically, if you want to know the details, you just kind of go look it up, but that's the answer. Briefly explain CHS addressing for disks. So what does CHS stand for? What? Cylinder head sector. Did you Google ahead? Yeah. Every time I hold a recitation, I time how long it takes somebody to figure that out. So it took you 66 minutes. Yeah, so CHS stands for cylinder head sector. The easiest way to think about this is if you look at a disk, so there's two ways to look at a disk. So the side and the top. So I'm looking at it from the side, or I'm looking at it from the top. If you're looking at it from the top, it's a bunch of concentric circles. So the data is in these concentric circles. So that's what. So the first thing you need to do is, if I'm going to get a piece of data, which of the circles is it in? Like which of Saturn's rings is this moon in? I got to go find it. Like how far do I go in? Right. That is the seek time, the head seeking in and out through the rings. The reason it's called a cylinder is, in general, in a disk, they're stacked. So if you look at them from the side, it kind of looks like pancakes gone horribly wrong. So, and the heads are all fixed. So you don't seek. When you seek, right, you're moving in and out of the same ring. If you think about it, like I've got a bunch of disks on top of each other. If I pick a certain ring, it forms a cylinder. So it's like the third ring in on 4 disks, it's a cylinder. So that's where the cylinder comes from. Now, historical note, they actually used to have, instead of disks, they had storage devices that actually were cylinders. It looked like a metal, like a hull, like kind of like, a piece of, like a roll of toilet paper, but the metal was on the outside, and they spun really quickly, and the head went back and forth on the cylinder. And the thing spun like hell. The problem is that occasionally they would break loose and go bowling in the data center. So they were kind of frowned upon for that reason, because occasionally they would break loose and one of them would go ripping through the data center, just plowing through everything. So I don't know that these things spinning is any better, but yeah, they would break loose and then all hell break loose. An A6 Intruder, which was an attack bomber, actually had one cylinder that spun this way and it would get stuck periodically. So the navigator would have to bang it with his foot to get it unstuck on a bombing run. So they were not really the most useful approach. So that's cylinder. That tells me how far in or out I have to go with the head. Head is, which of the disks am I looking at? Is it the top one? Is it the second one? Is it the third one? Is it the fourth one? Now, it's a little more complicated than that because in general, they put data on both sides of the platter. So when a head goes in, right, I mean, there's a head that's looking, so on a particular disk, if this is the disk, there's actually two heads that are going back and forth. One that'll read the top side, one that'll read the bottom side. So head is basically which side of which platter. And then sector is, well, if I'm looking at it from the top down, it's kind of the rings of Saturn. But if you think about it being like a pizza or a pie, the sector is the wedge. And so I've got to figure out, like my head is here, the head's fixed, I've got to wait until that piece rotates around under the head. And so that's cylinder head sector addressing. E-tag processing. Briefly explain E-tag processing. Have you Googled the head to E-tag processing yet? Okay. We're waiting. No pressure. I would consider that answer somewhat incomplete, but okay. Basically, if I do a get or a retrieve, so I retrieve a piece of data, and then I change that piece of data. Like, so I change, I retrieved, I don't know, a purchase order or something, and then I made a change in it, and I write it back. Unless I've locked it, there's a chance that somebody else updated it since I read it. So I read it, somebody else reads it, we both update it, and both of us try to write it back. Only one of those writes is going to succeed. The second one's going to overwrite the first one. Right? So what E-tag processing, now the obvious solution is that's a write-write conflict. What I should do is lock it. Well, locking, in general, you don't lock something that a person is looking at, because by computer standards, if I'm looking at this thing, I'm looking at it for 10 seconds, that's an eternity for a computer. And so if you lock things people are looking at, you can't make forward progress because everything's locked. So what happens on an E-tag is when whatever the server is, whether it's the web or something, it gives you the piece of data and it also computes a hash of the piece of data. So if I gave you 4K, a piece of data of 4K, I'm going to give you the data and I'm also going to compute a hash of that data. When you try and do a put, when you try and write the data back, you give me the new version of the data, but the value of the hash you receive. So now, when I'm trying to process the put, the write, I have the new data and the hash. What I do is I go read what's currently in the database and hash that. If that hash matches the one that I just received, the data has not changed, and I update it. If the hashes don't match, somebody updated that piece of data in between the person reading it, at which point I reject the update. And so literally what you're doing in a somewhat efficient way is you're saying, okay, you're trying to update this block. I'm going to go determine whether or not it changed. Right, well, how do you tell? You need the original version. Well, so the default behavior is when you try and do a write, you give me the version of the block you read and your updated version. I'm going to go read the one that's on the disk. If it matches your original one, that's fine. But that's inefficient. These things are large, and so they use hashes for it. So the essence of it is when you send the update and your hash, if the current state of the data matches the hash, no one's updated it, at which point you do the update. And by definition, that's optimal. You don't lock it, you abort, you undo a write when there's a conflict. So that's optimistic. All right. Is that clear to everyone? All right, so those are the 10 questions. Now, it's just that it's not even a statistical, but it's just a reasonable sample of the concepts we covered. And these, in my experience, are not uncommon things to come up in conversations or job interviews or that kind of thing. And so this is just, you know, if you can figure out a way to sort of mix key compression and sort merge join into your job interview, you know, or so these are just kind of things that are going to come up, because I could have asked you a dozen questions in a blue book, but even I don't remember this stuff most of the time. You can see, like, how does hashing work? I don't know. I could find a hash simulator. That's why God invented the internet. So a hilarious thing is when I was an undergraduate, there's a famous professor here, Samuel Eilenberg. He invented category theory. It's a branch of mathematics. He was teaching calculus 4. He would walk into the room, and when the lecture started, on the upper left-hand board, he would write the problem, and then he'd walk all the way across and write the answer on the bottom right-hand side. And then the entire lecture was how he got from the problem to the answer. After about a week of this, somebody finally said, okay, this is great, Professor Eilenberg, but what do you do if you don't know the answer? And he said, you look it up in a book. So, okay, if it works for calculus, it works for computer science. So those are the written questions. Are there any other clarifications on them? All right. And I did say you can look these things up. Just don't copy it word for word. I'd like to at least have the belief that you probably read it and thought about it enough to read it and then type it back in your own words, and just put a link to it. But again, just look this stuff up. All right. So back to the beginning, or request for the Redis one. Which one is the Redis one? Q7. Q7. All right, let's transfer pessimistic. All right, so I gave you this stuff. So I gave you this kind of code here. And this is kind of like a really wicked hint as to what the answer is. Because Redis treats keys as just strings. So this, you don't need to do this, but this is a tool I use, Redis Commander. And what happens is, in this case, if you take a look, there's person, colon, and a star. And then after that, there would be faculty. So this key for this particular piece of data is person, colon, faculty, colon, FED01. That's the key. This is such a common pattern that these are called branches. The fundamental thing people do is they taxonomize things. The person, well, there's two types of people. There's a student and a faculty. Right, this can keep going. How do you find all of the faculty? They have that I probably capitalized it, you know. So basically,
Yeah, basically,
you can see that there's only one key that matches that pattern. If I wanted to find all the keys of all the people, those are the keys for all the people. And so what happens is most inheritance diagrams are like trees. There's a parent, and then there's a bunch of children. And then they have a bunch of children. Well, that's all you do here is parent, and then you have the next segment is all the children, and the next segment after that's all the children after that, and the next segment. So it's literally like a branching in a taxonomy tree or a linguistic tree. So that's the pattern. Right? How do you find out if, right? Well, how do I compute what the uni is? Well, basically, let's go put a piece of code here. So I'm basically just going to go get uni. Go run that. What happened is it said, so if I go run this again, oops. That's the template it uses. I'm looking for something in the person branch. I don't care. Faculty, student, it could be faculty, tenured faculty, not faculty. It's in the student branch. Can have as many subtypes as it wants, but I want it to end in this, FVD0 star. All right. Well, that's going to tell me, how did I know that was the answer? Well, basically, how many of those did I find? I found one, so the next one must be two. So that's how you figure out what the uni is just applying that template. All right, so at that point, that's kind of trick number one. And I'll go find another one. This one's got the answers in it. When I store something, I just put all of the properties in that entry. Let's see what I can find the code. This damn thing so many times. Well, I mean, if you go back to Redis Commander, you can see that. Like if I go pick a specific one, all of the properties are in that one key entry. So technically, the way to think about this is that this is like basically this is like the one table solution. All of the properties for the type and its parents are in a single table. Now, if I ask for a base type, I just don't, in the code, I just don't return the ones that are part of that type. So if you ask me for person, I'd have a little piece of data that said, well, the fields of person are first name, last name, and email. Let's go see whether I actually found this one.
Hello.
So that's graph. So you see that this stuff I gave you, create faculty. It's got last name, first name, email, title. I get the next uni, right? So that's going to tell me the next number. There's 217 people that are in the person branch. This is going to be 213. And the key is person faculty 213. These are the properties, and I just add that to the cache. That's all you do. Create student is exactly the same way. This is the part where normally we take the family photos. So if anyone wants to take a family photo, everybody, we can do a movie if you want to do a movie, or all right. If you do person, you can just see that all I do is that in here I have what are the lists, the fields that make up a person, and if you ask for those, I don't return. I only return them. So that's how get person works. Pretty straightforward. The only other one that's the least bit tricky here is the advises relationship. And all I do for that is additionally, for everybody who's an advisor, there's an entry, advises, colon, and all that's in there is a list of the unis of the people they advise. So that's all that is. Which one? It's right here. Get advisees. So I'll run this. So basically, if I just add a cell here, I'm going to say and I go here and I do get advisees of FEP01. All right. So there's that. So if I run this, it just returns a list. So there are 3 fundamental types that you can store in Redis: a string, a dictionary, which they call a map, which is the JSON term for it, and a list. Now there are variations of those. So for instance, there's a set, which is basically a list where the elements need to be unique, obviously. There's an ordered set. But the 3 common types are it's just a string of bytes. It is a map, or it's a list. Well, normally, if I get a list, I'm going to go and get an element out of the list. But there's an operation range, which says give me everything in the list in this range. And following the Python convention, -1 means I don't know how long the list is. This means the end of the list. So this means starting at 0 all the way to the end of the list. Give me everything that's there. So, yeah. Just this one. The reason it's in here is I just did this for the heck of it. But if you notice, when I create a student, right, I just basically update it here. On the other ones, I actually checked whether or not it existed. But this one, I just did it. So no, you don't need to return it. But anyway, that's the Redis stuff. What other ones should I go over?
5, please.
I don't get a sales commission on Redis Commander, so I'm not going to make you use it. Whoops.
How should the diagram look like?
I want to do that one. So I want to do that one. Just gonna make a new tab here. Oh, that's a lovely color.
For Redis, do we have to include a diagram?
Basically, all you do is that's just going to show you the keys, and from that point, and then I can just this basically, what does this show me? This shows me that you understood the hierarchies, and also it shows me that you have the advisees thing, advises, that kind of thing. Okay. So that would do it. It's the only thing. It's come up a couple times on Piazza, but that's all you really need. All right. What else do I need to cover?
Could you go over number 5, please?
Can I cover 3.3?
3.5, please.
Just trying to remember which one 3.3 is. Oh, Christ. Not this one again. All right, so let's do these one at a time. 3.3. This one, the two extremes of using a relational database are online transaction processing and data-driven decision support. Online transaction processing has updates. You change account balances. You go and you add segments to a trip. So it has updates. And in general, the queries are relatively simple. Which is, if I go to an ATM, I'm not asking for the average account balance over all people in Bolivia in the past 3 months. I just want to know my account balance. So it tends to be very simple key-based queries, and it has updates. Because it has updates, you want to have integrity, which means you want to eliminate functional dependencies, because every time you have a functional dependency, you risk an update anomaly. So you get an assert, delete, update anomaly. So you decompose it. The way you eliminate functional dependencies is you split tables into two and you use joins. So that's how you avoid update anomalies, is by decomposing tables. On the other hand, when I'm doing queries, I tend to be looking at lots of columns trying to figure things out over lots of rows. I don't want to have to do a join. So for online transaction processing, you normalize the data and decompose, because that eliminates update anomalies, and it means you have referential integrity. On the other hand, when you're doing queries, you tend to want big, wide tables. So this exercise is build a big, wide table. So what I'm trying to do here is I'm trying to get a single row that summarizes a player's performance for their career. The performance data is in 5 tables. Salary, so how much were they paid in the years? Batting, how many hits, how did they do in a year? Fielding, how did they field in the year? Pitching, and how many games they appeared in. So if I wanted to pull together a record on a single player, I'd have to just join all these tables. I don't want to do that every time I'm trying to make a decision. So I'm going to go pre-compute the joins and put them in a wide flat table. So we're going to produce a table that summarizes a player's performance metrics. So these are the metrics: games, at bats, runs, hits, doubles, triples, home runs, runs batted in, bases on balls, and my specialty being hit by a pitch. Pitching games they pitched, wins, losses. For how many outs were they a pitcher? How many hits did they give up, and how many earned runs did they give up? And then fielding, the tricky thing on fielding is in batting, we've got that weird stint. So you basically have to group by player ID, year ID. So that one you can kind of flatten out. I'm just going to group by player ID. On the other hand, if I group fielding by player ID, in theory, I could wind up with 9 entries, 1 for each position the person played. That's not a wide flat table. So I get all the batting stuff into one tuple row, get all the pitching stuff into one row. I have to do unnatural acts to get all the fielding stuff into one row. So what I wanted that one is games, and then broken down. So I guess this one is outs as a pitcher, assists as a pitcher, errors as a pitcher, outs as an infielder, assists as an infielder, errors as an infielder, outs as an outfielder, assists as an outfielder, errors as an outfielder, outs as a catcher, assists as a catcher, and errors as a catcher. So I wanted it like that. So ignore salary and appearances. Ignore things prior to 2010. Now, don't include batting information for seasons in which the person had less than 100 bats. And if the player didn't have 500 career at-bats, don't include them. So if somebody didn't have 500 career at-bats, it's not statistically significant. I'm not going to include them. If they were injured for a season and only batted 3 times and they got 3 hits, I don't want to consider that 1,000 because it's just a fluke. So I'm trying to filter out bad years and not enough data. Same thing for pitching. And then same thing, just filter out statistically insignificant information. Like my example of this is, much to my surprise, when I was doing some of this, Ted Williams actually pitched 5 innings in 1945. Ted Williams was not a pitcher. If you had Ted Williams pitching, he would have been shot in Boston. So you just don't want to think this guy's a pitcher. He just not qualify as a pitcher. So I'm trying to filter out people who only caught. So make a copy table. You can create intermediate tables, blah, 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 blah. This is the answer that I get. So this is my wide flat table. Player ID, games batted, at-bats, runs, hits, doubles, triples, home runs, runs batted in, walks, intentional walks, never pitched, never won a game as a pitcher, never lost a game as a pitcher, never had outs as a pitcher, never gave up hits. Over all games, right? These were the outs, assists. So this probably was an outfielder. Assists, errors, infield games, infield outs. So I've just basically flattened it all out. So now at this point, I've got a single tuple that summarizes the players: offense, pitching, and defense, fielding. So that's what I want. I've filtered out people who haven't played enough games, or I filtered out years when they didn't do enough. So that was the specification. I would not have got hung up if you kind of mess some of these things up, as long as you just sort of, as long as you showed, yes, I know that we're filtering out career stats where there's not enough of them year stats. This is the script. So this is in here to give you a feel for what an ETL job might look like, extract, transform, load job. The way to think about it is these things are inherently graphical data flow computations. So I'm extracting data. So these are 3 extracts. They're doing selects. Select on batting, select on pitch, and select on fielding. This step is the extract. This is a transform because I'm basically doing aggregates here. So I'm aggregating the things up. So what comes out is different from what comes in. And I stage it into an intermediate table. Then there's another load, and I do a full outer join, stage that. When I get here, I load that and that. There's another full outer join. That's the answer. So this is what these this map reduce jobs might also look like this. But anyway, this is the one that's a nightmare, is because you're basically having to take lots of rows and kind of just append them and append them and append them. And so if you go and you look at the script, this is the script that built that wide flat table. Goes on for a little while. So, you know, sort of when I got through that, I figured I would have to extend the final deadline to June if I wanted you to do that one. So what I just basically said is do this little flow here. Right? And there's really 3 queries involved. There's this one. So if you look at it, I'm gonna create a table batting summary. This is gonna be a player's career batting summary. So I'm gonna select player ID, the sum of the games. How many games did they play? The sum of the at-bats, some of the runs, some of the hits, some of the doubles, some of the triples, some of the home runs, some of the runs batted in, some of the walks, some of the intentional walks, right? Only in that range. So I'm only going to look for years after 2010, and I'm not going to consider years where they had less than 100 at-bats. So that's going to filter out years where they didn't play enough. And I'm only going to include in the result people who had 500 career at-bats. So this phase is going to filter out years that were anomalies. This is going to filter out people who didn't play or get enough at-bats. Same game down here, literally basically the same idea. Create the pitching summary. What are the metrics that I want? Don't look at years before 2010. If they weren't a pitcher for at least 50 outs in that year, ignore that year. And then don't include people who did not pitch for at least 150 outs. So that's this. Right. This is just the full outer join of those 2 tables. And the reason it's a full outer join is some people batted and some people didn't pitch. Some people pitched and some people didn't bat. If I left join, I'll get everybody who batted, but I could lose pitchers. If I right join, I'll get people who everyone who pitched, but I might lose batters. This way, this is how you get that answer where you actually ever look at these things when you scroll through them. What happens is there's a quadrant up here. So this is data, null, right? And then there's going to be data on both sides, and then null and data. So basically, which ones are in the left but not the right, which ones were in both, which ones were in the right but not the left. So you get this weird thing where at the top, one half is got data in it, the other one's got none. Then there's a segment where all the columns are filled out, and then the bottom on the left-hand side's done, the right hand isn't. And this one is because some of the students on the midterm were smart enough to figure out how to answer the question that I gave them without doing a full outer join. So I came up with a question that was impossible to solve without a full outer join. So you can blame the students who figured it out on the midterm because you were not getting out of this class without doing a full outer join. All right. So that's all you need to do for this. Is that clear? And if you want, and literally they're all in here. So if you go down here somewhere, I showed you the two. And then if you go, I think it's this one. Yeah, this one is, you would not actually, because I created a temporary table here because I was actually rolling this up to get the full table. But this is basically the outer join that produces the answer. So you can see literally what's happening is that I'm just doing a left join and then a right join and then taking the union. And so that's the query statement that'll actually do the full outer join. Right? Yep. Is there no prettier way than what? You would think that there would be a nicer way, wouldn't you? But no, as far as I can tell, there isn't. So first class pain in the butt. By and large, we have not used them, but people will typically use tools for this. So you're basically just pushing buttons. So you don't have to actually type it. It's just radio buttons, that kind of thing. But so no, I've actually, number of times I've sort of sworn at my friends who designed this because of that. Literally, it's sort of, I mean, the one that drives me crazy is I'll do a join and then it'll complain about duplicate columns. At which point, what I really want to say is all of the ones on the left and then the ones on the right that don't appear on the left, there's no easy way to say that except enumerating them. It's a pain in the neck, but yeah. So I can't think of any other way to do it. All right, so that's that one. All right, and we will do one from the audience and then wrap up.
Go over 3.5, please. Hello? Can you hear me?
All right, so no particular order. So I just randomly picked the first one because that's as good a place to start as any. What?
I think it's because on your example, you have all the pictures having.
They're very good pictures. It's probably a bug in it.
So our answer set.
Okay, it's fine. I was like, when I started getting to the bottom of that script, I just wanted it to be over at this point. So yeah. So get order. This is the query that does that. It's literally joining order and order line or order details. So I just join order and order details on order ID. So, I mean, if you just, we'll just sort of just comment this stuff out, the rest of this stuff out here. So basically, I'm just going to comment this out for now. And I'm going to return the result. So we'll go run that. And then we will go run this. Test Q. Name run Q is not defined, so you need to go way back up here. Go run this one. Syntax is not defined. Syntax is equal to. So when I run that join, does exactly what you think. So for that order, it gives me back a row in the result for every order detail. The problem is that these fields are repeated for every single one of them. So it looks kind of weird. It's not what an order, when you request information for an order, right? You don't expect it to sort of have this thing over and over and over again. What you expect is this appears once, and then in the table, that's all you see. So if you ever seen like, you know, an order, if you ever look at your order from Amazon, it doesn't have your address on every item. Okay, it's like got the header stuff up, and then it's got the entry for each one of them. So what you need to do in this one is just say, I'm going to post-process it. And so what I'm going to do is, assuming I got an answer, out of the, where'd that go? So assuming I got an answer, I know that in the first answer, these are the 4 common things. So I just go pull those out of the first one, right? And those are the things that go in the the header. All right. And then I'm going to have a list of all the other ones. So then I'm just going to go through those and put them in the list. And so that's all on that. And you're on that. So you can see the common things appear once, and then all that happens in the repeating section are the things that are specific to the order details. So you can get it with one query, but you have to post-process it. And the reason I did this one is on the web, and to some extent, when things get put on paper, it's hierarchical. There's like a header and then a subsection and then a subsection. Relational data is tabular. And so the queries produce tables, but whenever you do a join, you denormalize the table to get redundancies. So to show it in a normal form, you basically have to go and factor out the common things. So that's all you needed to do for the first one. All right. Oh my God, I feel dumb. I spent 3 hours on that trying to return the product list directly, exactly as the example looked with no post-processing. Thank you so much. Okay, A, you're welcome. B, that was private, so I probably shouldn't have shown it. And C, I repeatedly told you if you spend several hours banging your head against something, you should come out and ask for help, because there's no value in you banging your head against something for a long time. All right, so we'll wrap up here, and I will continue recitations tomorrow, Saturday, and Sunday. All right.
So I'm going to cover the 3.9 and 10.
Not now.
No, yeah, tomorrow. Yeah, I mean tomorrow. Or Saturday.
No, I'm going to explicitly not cover those two. Yes, I'm going to cover them. I've covered them 3 times already. Why wouldn't I cover them again? Yes, I'm going to cover them. 3.9 and 3.10. Those ones are actually, so what are they again? Yeah, I'm going to go over them. I'll leave it. So basically, what'll happen is
It's not covered last time.
what?
It's not covered last time.
I've covered it at least twice. You just haven't come to the section, so I covered it, but yes, I will cover it. All right.
Thanks.
Yeah.
Professor, could you please, I posted on Piazza and I can update, I updated